Hello everyone, I'm Sebastian Y, and this is Managerial Economics. In this video, we're going to talk about cost functions. Now that we've learned how to minimize costs for a given target output, we're now going to look at what happens to total cost as Q changes, assuming we are going to continue properly cost minimizing. This leads us to the cost function denoted C of Q. The cost function is very important in managerial economics, and we're going to be continuing to use it all the way to the end of the course. Later on, we're going to be doing profit maximization in a variety of different contexts, and the cost function is an integral part of that. Let's review a few terms. Fixed costs are costs that are unaffected by the quantity choice, whereas variable costs are affected by the quantity choice. Fixed costs are going to be the costs of fixed inputs, and variable costs are going to be the costs associated with variable inputs. Total cost is the sum of these two. In the first video in this set, we distinguished between the long run and the short run. We're going to start out talking about the short run, where capital is fixed at a certain level that we're going to call K star, while labor is free to be chosen by the firm. To illustrate this, we are going to return to our example Cobb-Douglas production function, which was K to the 1/2, L to the 1/2. We will assume that in the short run, our capital is fixed at 25. To get our short run production function, which is just f of L because K is already chosen for us, we're going to plug in 25, simplify that down to 5L to the 1/2. To minimize costs, we're going to set this equal to our target output Q. Then we're going to solve for L to figure out what our quantity of labor needs to be. So I'm going to divide both sides by 5, and that's going to give me L to the 1/2 equals Q over 5. And then I'm going to square both sides to get L equals Q squared over 25. This is going to tell me exactly how much labor we need to use for any amount of Q. To figure out our short run cost function, C of Q, we're going to have R times K star. That's going to be our fixed cost. And then we're going to have our variable cost of WL. From here, we'll suppose that R is 10 and W is 5. We'll plug in all the numbers. R is 10, and we know that K is 25. W is 5, and L, we are going to plug in the L that we solved for before, Q squared over 25. This is going to come out to 250 plus Q squared over 5. Thinking about this equation a little bit more, fixed cost is the part that does not depend on Q, so that's this part right here, and the variable cost is the part that does depend on Q. We'll now continue on with a few definitions. In the short run, we have three types of average costs. Average fixed costs, or AFC, is defined as fixed cost divided by Q. Average variable cost is defined as the variable cost divided by Q. And the average total cost is the total cost divided by Q. Note that all three of these things are functions of Q. In our example, fixed cost is 250, so we have 250 over Q. Our variable cost was Q squared over 5, and we're going to divide that by Q. One of the Q's is going to cancel, and it's just going to be Q over 5. And our average total cost is C of Q over Q, which is also equal to the average fixed cost plus the average variable cost. So in our example, that's going to be equal to 250 over Q plus Q over 5. To do one last definition, we have our marginal cost. As always, whenever you hear marginal, think derivative. So what this is going to be is the derivative of the cost function with respect to quantity. In our example, we have the derivative of 250 plus Q squared over 5. Derivative of 250 is 0, and the derivative of Q squared over 5 is going to be 2Q over 5. Cubic cost functions are a common algebraic form that we will use. Cubic cost functions look like C of Q equals F plus AQ plus BQ squared plus CQ cubed. Because we have a cube term here, that's why it's called the cubic cost function. The cubic cost function is quite versatile, and it can be used to approximate much more complex algebraic forms. F, A, B, and C are just constants. If we were to calculate the marginal cost of a cubic cost function, it's going to be MC of Q, and we take the derivative of each of these four parts. Since F does not have a Q in it, that drops out, and we go from there using the power rule. So we're going to get A plus 2BQ plus 3CQ squared. I'm going to sketch a graph of what cubic cost curves tend to look like. I'm going to graph all three of our average costs as well as our marginal cost. I'm going to put Q down here, and our various costs will be on the vertical axis. First of all, the average fixed cost is always decreasing. It's just a constant number divided by Q, so it's going to be constantly going down. The marginal cost tends to initially drop and then increase from there. The average variable cost has a bowl shape where the bottom of the AVC is also where it crosses the MC. And finally, the average total cost is the sum of the average variable cost and the average fixed cost. Because the average fixed cost is so high, average total cost will also start out quite high, but it's going to come down as average fixed cost comes down, but of course, average variable cost is coming up, and that's going to start pulling it up as well. Average total cost also crosses marginal cost at its lowest point. Because average fixed cost is dropping as Q gets bigger, ATC and AVC will get closer and closer together as Q gets larger. The point at which ATC crosses MC is the point where average total cost is as low as possible. This is called the efficient scale. If we think about the reason why this happens, remember that marginal cost is the amount that cost increases as we increase quantity. If the increase is below the current average, like it is at this point right here, it's going to be pulling the average down. If the additional cost is above the average, it's going to be pulling the average up as it is over here. So the point where they cross has got to be the lowest point of ATC. A way to conceptualize this is to think about if you were to get a grade lower than your current GPA, your GPA would come down. If you got a grade higher than your current GPA, then it would come up. Note that our example short-run cost function fits into the framework of the cubic cost function as well, but A and C are both 0. Let's find the efficient scale of our example cost function. We found above that the marginal cost is 2Q over 5, and the average total cost is 250 over Q plus Q over 5. We know that the efficient scale is where marginal cost and average total cost cross, so we're going to set 2Q over 5 equal to 250 over Q plus Q over 5, and then we're going to solve for Q. To do this, I'm going to subtract Q over 5 from both sides. So 2Q over 5 minus Q over 5, it's just going to be Q over 5. And we're going to get 250 over Q over on this side. I'm going to multiply both sides by Q and both sides by 5 to get Q squared equals 250 times 5. 250 times 5 is 1250. And then I'm just going to take the square root of both sides to get Q equals square root of 1250, which is approximately 35.36. So if we were to draw a graph, what we would have is a marginal cost curve that looks something like this. In this case, it's a straight line. It's just 2Q over 5. Then our average total cost curve would have its lowest point at efficient scale of 35.36. The last thing we're going to do in this set of videos is talk a little bit about the long run. Remember that the definition of the long run is when capital becomes variable. It's no longer fixed. This is going to allow us to choose capital and labor when cost minimizing, just like we did in the previous video. Supposing that we are able to do that, we can then draw a graph of our long run average total cost curve. I'm just going to draw an example long run average total cost curve. It looks something like this. We are able to choose K perfectly for any level of Q. So the long run average total cost represents the lowest possible average total cost for any given Q. But in the short run, K is fixed. In the short run, average total cost is always going to be at least as high as long run average total cost. If we draw in some short run average total cost curves, each of these short run average total cost curves corresponds with a particular level of capital. This first one I drew has a relatively low K star. The one I drew over here has a relatively high K star, and the one in the middle has a medium level of capital. Each of those levels of capital is the perfect amount of capital for one particular quantity of output. And that is the quantity at which these curves are tangent to the long run average total cost curve. Once we move away from that quantity in the short run, it becomes less efficient than it would be in the long run because we're no longer using the cost minimizing amount of capital for our chosen level of output. With our low amount of capital, we eventually get a high enough amount of output where it would be worth it to have had the medium amount of capital. And as quantity goes up from there, it eventually becomes worth it to use the high amount of capital. And these are only 3 examples. You can imagine an infinite number of these short-run average total cost curves sitting there inside the long-run average total cost. There are a few terms that we use to talk about long-run average total cost. If long-run average total cost is decreasing as quantity increases, and that happens to about this point right here, then we say that there are economies of scale. Average total cost is dropping as quantity increases. That is, there are efficiency gains associated with getting larger. With this classic U-shaped average total cost, we eventually hit a point where things start to become less efficient as quantity increases, and this is called diseconomies of scale. The final case would be if long-run average total cost is flat, then we have constant returns to scale. If we go back to the Cobb-Douglas function, f of kl equals k to the a, l to the b, there is a relationship between these exponents, a and b, and returns to scale. If a plus b is greater than 1, then we have economies of scale. If a plus b is less than 1, we have diseconomies. And if a plus b equals 1, then we have constant returns to scale. In our example, a and b were both 1/2. That adds up to 1, so we have constant returns to scale. What this means is that doubling the output is going to double the cost. That means that average total cost is going to stay the same, and that's going to correspond with a horizontal long-run average total cost curve. And that is it for the production process and cost. Make sure you're feeling comfortable with this material before we move on, because we are going to revisit concepts from these videos as we move forward. If you have any questions, feel free to let me know. Thanks for watching.